Okay, good morning. We'll get started again. We were discussing the two-stage op-amp, which consists of any single-stage op-amp followed by a common source amplifier, right, with an active load. Now, this can also drive resistive load. So, this is actually the most commonly used type of op-amp. And if you need even more DC gain, then you can use even more stages. But then you can go on adding common source amplifier stages. Okay. So what we saw was, yeah, I think we evaluated all the relevant parameters because the output stage has just two transistors, one to the top and one to the bottom. It provides the maximum swing that is possible, just one VD sat away from either rail. We also evaluated the slew rate. The slew rate is basically determined by cutting off some transistor cutting off. Basically, you're trying to make an integrator. What the integrator does is you converts the input voltage to a current, and that current is passed through a capacitor. Now, in any stage, because of bias current limits, the current that can be driven into the capacitor will be limited. Some capacitor. In this case, it is this CC. So that limit can come from either the first stage or the second stage. So here we evaluated from the first stage you get some limits, and also in the second stage this M11 can cut off because its current is variable. So that poses another limit. So based on that, basically you can determine the slew rate, or at least you make sure that it's not limited to small values by one stage or the other. Okay. So that is about the two-stage op-amp. Invariably, the GM2 will be the second stage transconductance will be more than the first stage. This we have seen earlier also to keep the zero beyond the unity loop gain frequency and so on. So the second stage will have you design the second stage to have a larger GM than the first stage. Okay, that's usually the case. And of course, noise and mismatch are dominated by the first stage. This is what you expect in a cascade of amplifiers. And the input swing limit is whatever is determined by the first stage. Okay. So if you want a two-stage amplifier, a two-stage op-amp with a rail-to-rail input common mode range, then you should put that rail-to-rail input stage as the first stage and then followed by the second stage. Okay. Any questions about the two-stage amplifier? Now here on, so if you wanted more stages, what you could do is the following. You add another stage. Now, of course, after this one, I mean, it doesn't matter whether it's NMOS or PMOS, we choose whichever one is convenient. Okay. So let's say, just for argument's sake, I use an NMOS third stage. I call this M21 and M22, and this bias comes from some current mirror. Okay. So the M22 is a current source basically. It is the active load for M21 and it comes from a current mirror. Okay. Now, of course, we know that to turn this into an integrator, we need CC over there and then another CC2. Okay. So basically, this GM1 is driving this integrator, and that integrator has another integrator inside it. Okay. So this is a what is called a 3-stage Miller compensated op amp. Sometimes it's also called nested Miller. Nested means one inside another. So that's basically what it is. Okay, and you can keep going. Basically, now you know how to design this at the level of GMs, so you can keep changing this. Okay. Any questions here? And of course, in a stage like this, you expect that the GM of the third stage will be larger than the GM of the second stage, which is larger than the GM of the first stage, and so on. So typically, you go to more stages only if required. Okay, that is, there is some penalty. There is a power dissipation penalty to going to more and more stages. So you do that only if it is required. Okay. So this, yes, right, that's correct. Yeah. So here, the input of the op amp, this will be minus, that will be plus. Now, how do these op amps get biased? Because of course, if you leave it in open loop, it is not going to be biased correctly. And in any case, especially with random mismatch, it's guaranteed that the output will be near the upper or lower saturation. Okay. So again, I'll consider unity feedback. The feedback need not be unity, but so let's say I connect it up like that. Okay. And then this is at some Vref or V bias. This is equivalent to that one, right? Now, let's say for instance, how does this M11 get biased? You can think of it as you have M11 and you have this current source I12. I mean, this M12 is basically a current source, right? Made using a current mirror. And you can think of the rest of the circuit. Okay, what is the rest of the circuit? Sorry. As whatever is used for biasing. I think when you learned about biasing of single transistors, you know that it is biased using negative feedback, right? Based on this voltage here, okay. So for instance, if the current through M11 is more than I12, then this voltage tends to increase. So then you feed it back to the gate of M11, right? That's what we were doing. Now you can feedback directly, that is you just connect a wire, that's the diode connected device, but it doesn't have to be. You can connect it through any stage that has a positive incremental gain. Okay. So now the rest of it can be thought of as the circuit for biasing this. Okay. So if you look at what is there, that is what is happening, right? If this voltage increases, the gate voltage of M11 increases. Okay, that will reduce the current through M11, and eventually M11, the drain current through M11 will be the same as I12. Okay, and if you have many stages in feedback, I mean every stage you can sort of consider this from a selfish point of view that the rest of the circuit is there only to bias it, right? So you can think of this. Of course, that's not the point of this. There is an op amp here, but like just from the point of view of biasing M11, the rest of the circuit is there to provide negative feedback. So once the op amp is in negative feedback, all the stages will be in DC negative feedback and each one will get biased correctly. Okay. The same goes for M4 and so on. Wherever you have two current sources connected together, ideal current sources, unequal values, it doesn't work at all, right? I mean, it just violates the basic circuit laws. If you have transistors, of course, the transistors will not be ideal current sources to begin with. And in any case, once it moves to the triode region, it's not a current source at all. It's a low impedance, low resistance device. So that is what is going to happen. It is going to go out of the desired range of operation. But it's only when you place the op amp in negative feedback that all the transistors remain in the saturation region. Now, of course, as far as analysis is concerned, many times you have to do analysis in open loop, but then you assume that the transistors are in the saturation region, but then eventually you have to verify that when you place it in feedback, they are in the right regions of operation. The same goes for simulations also, right? Whenever you do simulations or breadboard experiments or anything, the first thing to check is the operating point, okay? Because let's say you do the analysis and then you do simulation and then you say, oh, but the gain is not, or transfer function is not coming out to be what I want it to be. But then the first thing to check is whether all the transistors are operating in the correct regions, right? Because if they're not operating in the correct regions, if the operating point is not set correctly, everything else also will be wrong, okay? Any questions about these op amps? This this type of op amp is sort of the most popular one. I don't know if you have seen the data sheets of op amps. Let me see if I have it here. The tour, like the city tours, right? So you have used op amps in your labs, okay? I don't know if this is which one. Which op amp did you use? What's the number? What's that? 741. Really? The undergrads use 741 here. Do you remember this or no? I don't know. Maybe you could have, but 741 is so old. I thought you were. Didn't you what supply voltage did you use? What is it? Ah, yeah, MCP 06 or 60 or something. I think that's probably what you would have used. But I think I don't know if I have a picture of that. This 324 is a quad op amp. I've used that in the past. So this is the picture. One thing, of course, is it is with bipolar transistors, but you do know that bipolars and MOS and small signal wise they are the same. So what can you identify here? I mean, does anything look recognizable after all these lectures on op amps? Huh? Huh. Okay, some symbol that's recognizable. I mean, not some symbol, some notation, right? What is it? The what? PNP, right? Okay, that is, they have used, I mean, it's the equivalent of using a PMOS differential pair. Okay, there is a reason for this. I will explain, but anyway, that. CC, right? I've been writing CC in all these lectures, so at least you can see some capacitor named CC. Okay. So now, of course, when they make commercial op-amps, they also have to take more care than when you make an IC op-amp for your particular circuit, because who knows who will connect what into it, right? So this, one of the things with bipolar transistors is the input current is not zero. The input resistance is not zero. So if you make a bipolar, if you make a differential pair with bipolar transistors, what will be the input impedance, input resistance? 2 times R pi. Okay. So a common source amplifier will have a resistance R pi. It will have 2 times R pi, which can be quite small. So here, if you look at this, what stage is this? Can you recognize? Voltage follower. It's basically a PMOS emitter follower. It's the equivalent of the source follower. Now, how is it biased? It looks like there is no bias current. But the thing is, the following transistor's base current is the bias current for this. Okay. And you can see, I think this is 6 microamp probably. 6 divided by beta of this is the bias current for it. So basically, you get a fairly high but not infinite resistance. Okay. These are like really old op amps with bipolar transistors, but basically that's what it is. And then you have essentially it's a buffer followed by a differential pair, and then you have the same current mirror here. So this part is clear. And again, if you look at, so this whole thing is the first stage. And now what is this? Seems like some extra. What stage is that? What is Q10? What is Q11? Q10 is basically a PMOS emitter follower or a source follower. Q11 is also an emitter follower. Basically, this whole thing is a buffer before the second stage. So again, because you have substantial base currents in bipolar transistors, you have this. Okay. But finally, Q12 is the actual second stage. It's a common emitter amplifier biased from a current source. Okay. Otherwise, what happens is if the impedance of this loads this, the gain may be substantially reduced. You can see this is operating with a 100 microampere current, whereas this is operating with a 4 microampere current. So the input resistance, and this is anyway an emitter follower, so the input resistance will be much higher. So now you have the second common emitter amplifier, same as common source amplifier, with CC across the second stage. Okay, so that is the integrator, right? So it's exactly what I have been showing, except I mean, if I had showed a PMOS differential pair with an NMOS common source amplifier in the second stage, it would look even more like this. Okay. But of course, after that, it is different in that there is this buffer. So there is a big NPN buffer and a PNP buffer. This is required because this is a general purpose op amp. Who knows what you will drive with it, right? You could drive very heavy loads with it. So that's why there is a very strong buffer. And not only that, there is this resistance. This is so that, of course, you go and connect this to wherever you want, and then you don't want to burn out the op amp. What this does is, if large current tends to flow, it turns on this Q7 and shuts down the op amp. So this is all protection for general purpose operation. Okay. I'm sure you have done this, right? Shorted the output of the op amp. No? Never. Okay, I don't believe you. I mean, I can believe that some of you have not done it, but all of you have not done it. I somehow doubt that. Okay, so basically it's a 2 stages plus output buffer. You can read, at least the older data sheets have complete schematics. You can understand them. And then this is something that I would use when I was conducting the lab. It is similar, but now this is the simplified schematic. This is a weird looking transistor, but it's the same. You can understand what it is. The diode connected transistor is shown as a diode. It's really a diode connected transistor, that's all. And this, whatever the symbol is, it's called a junction field effect transistor. Probably you have not encountered it, but you can just think of it as a PMOS depletion mode device. That is PMOS transistor, but with a VTP less than 0. That is, with a VSG of 0, it will be on. That's all. So that's a small difference. So now the good thing about this is it has infinite input resistance. So that's why it was used. Now, of course, these are simplified schematics. The actual schematic looks something like this, but all you need is patience. That's all. So it's the same. It's the same circuit. Okay. So you can identify the input pair, and this is a current mirror, and I think you can recognize this also. Instead of the diode connecting this directly, it is through another transistor voltage follower. Again, it is to make sure that otherwise the base current is taken out of this, right? You have mirroring error. So to avoid these things, you have all of this stuff. And the second stage, again, you have emitter follower buffer followed by a common source amplifier. And again, you can see CC across it. That was actually the main thing I wanted to show. This architecture, this two-stage Miller type op amp is the universal op amp. What? Oh, oh, why is it like this? I don't know. I don't think maybe the full screen is not required for this. Very strange. What is happening here? On the other one, it's fully visible, right? Yeah. Okay. I'll just share the presentation. I don't know if I can make this. Okay. So here also there is some overload protection. I won't go into it. Basically, you have these series resistors. If too much current flows through that, it activates some other transistors, which shuts down the op amp. Okay. So that is again 2 stages plus output buffer. And this looks weird. I don't know why they use the symbol with the bipolar transistors. It sort of mimics the structure, but basically it is multiple transistors in parallel. That's all. This looks slightly different. So, but again, you can recognize the input differential pair. Okay. And the second stage is also a differential pair. I'm not sure why they used it like that. Maybe for convenience or biasing. But instead of using a common source amplifier, they have used a differential pair, but only one side output is used, as you can see. Okay. So you can again see this. This is the Miller, that integrating capacitor. Okay. And after that, you have the some buffer followed by the output stage. Okay. And one more thing I didn't mention, this balance, basically this is there so that this is also used in very high precision applications. So you will get some random offset, but you may want to null that thing. So by connecting different resistors to this, what you can do is you can inject small currents here, which are different from each other. So that means that you can effectively zero the offset. Okay. So if you want a zero offset in some case, you can use that. So that's why it is there. You can read the data sheets. I think especially with bipolar transistors, if you know the bias current, you know the transconductance and everything. So you can actually get a lot of information right out of the data sheet, and you can assume some random beta, let's say 100 or something, and go on with your calculation. Okay. So that the main point is this architecture is very, very common. Okay. Used quite a lot. There is one disadvantage here. Let me. This is the load, and that's the load current. Okay. So, like I said, you can use this with both resistive and capacitive loads. It's actually used when the loads are pretty heavy, meaning load impedances are quite small. So now, what are the limits on IL? How much current can you pull out of the op amp? How much current can you push back into the op amp? Most you can pull out is, yeah. So what happens is that, see, this is I11 is IL plus I12, right? So if IL is positive, there is no problem. There is no problem in the sense, of course, eventually it will get limited, but no transistor turns off. Okay. What happens is if you keep pulling more and more IL, more and more current will flow through M11. Okay. Whereas if you do it the other way, if IL is negative, if you are pushing current back into the op amp, what happens is that at some point M11 will just cut off. Okay. So if the load current exceeds I12, right, M11 will cut off. Then the op amp is not working at all. If the second stage is cut off, I mean, there is no second stage. There is no negative feedback, nothing like that. Okay. So now, how do you choose I12 then? You have to anticipate the highest load current that you will have. Let's assume typical sinusoidal cases. So that means the positive and negative peaks are the same. So you have to make sure that your bias current in the second stage is higher than the highest possible load current. Okay. This is regardless of whether you are using that current or not. Okay. So now the problem is there are many cases in which the it is being used in an idle mode. That is, the signal may not be there, or I mean, this is very common, right? You have an audio amplifier. It's not that you are driving it with the highest amplitude all the time. Okay. Only on some fraction of the time you will have the highest amplitude signal. Otherwise, it is just idle. Okay. Almost every circuit is like this. The same goes for RF power amplifiers in your mobile phones and so on. It's not that it is always in the transmit mode blasting the maximum power. So a fraction of the time it will be either idle or transmitting very little power. I mean, basically delivering a small IL. So it is important to so basically this leads to power inefficiency, right? You are wasting power when it's not required. So if you had an architecture where you have a small quiescent current, but you can deliver a large load current, that would be better. Okay. By the way, so let me just write this down. Okay. So this type of biasing, this is called class A biasing. That is, you choose your bias current so that it works for all the conditions, and the same bias current is there even for zero signal. Okay. So essentially the bias current is not dependent on the signal. This works very well as far as the transfer function and so on are concerned. Only disadvantage is its power inefficiency. It's very inefficient. Okay. So people have tried to come up with other biasing techniques where the quiescent current is small, but as the signal increases, right, the current, a higher current can be delivered. Okay. Now there are many such techniques, but I'll just go to one, and we can get a hint right from here. Here also, it's only the negative values of IL that are a problem, right? That is because this current is fixed, whereas the current coming from the top, that is not fixed, that is dependent on the signal, right? That is driven by the previous stage. So if a larger current is required, essentially the negative feedback will drive this gate downwards and then push more current through the load. That is basically what is going to happen, right? So in general, any output branch can be represented like this, with some connection to the top and some other connection to the bottom. Now in this case, what we have is a fixed current on the bottom, but a signal dependent or a variable current on the top. Even that variable current will be limited because you can't have unlimited voltage at the gate, but at least it can be dependent on the signal. Okay. So now if we want to not be, limited like this, that is, in this case we have a limitation on the negative load current. What is it that we need to do? What kind of arrangement would we need? Both of them have to be signal dependent. Okay. Both the upper current and the lower current have to be signal dependent. Okay. So this is basically what is class A, and it's limited on one side. But if you have signal dependent current on both sides, then you can potentially not be limited like this, at least not be hard limited like this. Okay. And this type of biasing is in general called class AB. These are some old terms. Okay. Now this is a very general description to say that the bias current should be dependent on the signal. The current should be dependent on the signal on both sides. But how do we arrange that? Okay. So I will so the gate voltage of this is some VG11, and it has the output of the first stage as the signal. The gate voltage of this is some fixed VG12. Okay. So what is it that I need to do so that I'm not limited by the fixed, I don't have that fixed current limitation? What should happen? Yeah. So basically, what I can try to arrange is this, right? If I do that for the second stage, that is, This is again not an unfamiliar circuit because I've drawn it as a part of the op-amp. It may look unfamiliar, but you have seen this, right? Pretty sure you have seen this. This is just a, this is the output structure, and you can think of it as a PMOS common source amplifier with an NMOS active load, or an NMOS common source amplifier with a PMOS active load, depending on which side bias you keep fixed, and which side you apply the signal. Okay. So if you apply the signal here, it's a PMOS common source amplifier. If you apply the signal there, it's an NMOS common source amplifier. I'm pretty sure you have seen the variant where you apply signal to both sides, right? The same signal can be applied to both sides. What happens then? What will be the transconductance of the second stage if you apply signal to both? It will be the sum of the GMs, GM11 plus GM12. That is also a good thing. Okay. Is this okay? So this is something that can be done. That is, you try to apply signals to both. Okay. Now, how do we bias the stage then? VDD by 2. Bias which one? I'm talking about this VG1 here is whatever is provided by the first stage. Earlier, I was deriving this VG12 from the current mirror when I wanted a fixed bias. Now, what should I do? What should I do? You have seen this circuit, right? When you discussed active loads in the previous course. What was the simplest realization of this biasing? You can bias them at the same voltage. That is, you make VG1, VG11 equals VG12. What circuit is it then? CMOS inverter. That's fine. So that can work. So one possibility is to do this. Okay, you just connect these two, right? So you can do that, but what is the disadvantage of that? No, they are the same. That is okay. But what is it? One is, of course, now because these two are the same, you have a compromised swing limit as well. Okay. Now with very low supply voltages, that may be okay because anyway you are not getting very high swings. That is one problem. What is if you connect it up like this? In the earlier case, what was the bias current in the second stage? I12, right? So it was known. It's very well controlled. Now, if you have a circuit like this, what is the bias current? What does it depend on? So if I do this and then, again, you must have calculated this. What does the bias current depend on? No, both are the same, right? And then let's say you bias them in the saturation region, or you self-bias this. Self-bias meaning you connect the input and output. What will be the operating point current? Huh? It will depend on the supply voltage, actually quite strongly. Okay. This is like going back to constant VGS biasing, right? Okay. So if the transistors were identical, meaning their mu Cox W by L were the same and the threshold voltages were the same, if you self-bias them, it will get biased at VDD by 2, and then you can calculate VDD by 2 minus VT whole square, that will be the current. Okay. So in general, if you look at this, if you connect it up like that, the current will be dependent on VDD minus VTP minus VTN square. The proportionality constant will be something complicated, you can calculate, but it will be very strongly dependent on the supply. And the other feature of the CMOS inverter anyway. The CMOS inverter's current is strongly dependent on the supply. Okay. So this will deliver the signal to both stages, both PMOS and NMOS transistors, but it doesn't have a well controlled bias current, and it also has the swing limit issues. Okay. So what else could we do? Actually, it's not that simple, because you would like the voltages to be the same, but you don't want this uncontrolled bias. Now, there is one more thing that is possible, that is, this is again only in limited context. You can actually use AC coupling. I already said earlier that normally inside an op-amp you prefer not to do it, but if that is permitted, at least for one side of it, you can use AC coupling. That is, you use some large R bias. So now the operating point is the same as before, right? Nothing has changed. Only thing is, the signal is also connected there, so that if you have a AC signal swing, the same signal appears there. Okay. And of course, you have to obey all the rules of AC coupling. That is, you have to make R bias times Cx large enough so that this network works for your signal frequencies. It will for sure not work for DC, and even getting it to work for very low frequencies may be difficult, meaning you may need very large R bias and Cx, which may give you other problems. Okay. Is that fine? So that is something that is that can be done. Now, let's say if AC coupling is not allowed at all, you want this to work for DC. There was a weird structure in one of the assignments. Let's see what it does. So it's actually a non-trivial thing to do. Like this structure is used for it. I had just given it as an isolated circuit analysis problem, and I think you would have found that what was Ri? Do you remember? Infinity. It has only current sources. So the thing is, it should still look like a common source amplifier. The input resistance should be infinite, because there are ways of fixing the bias current, but then completely ruining the signal picture. Okay, that's not what you want. You want it to behave like a common source amplifier. Now, you applied Vi. Again, I used AC coupling just for simplification in that problem. What was the, do you remember the signal swing that appeared here and there? No? Both are VI, I think. You probably have found that both are VI or something like that. Okay. So somehow this structure, right? This works like you have these two transistors. In this it is M4 and M3. Okay. So now, or maybe I think I'll continue with this a little later. But first thing is, as far as operating point is concerned, you can see you have VGS of M1 and then VGS of M3. Okay. So if you bias it like this, that is, I'll label them as M1X, M3X. It means that this is a replica of M1, that is a replica of M3. Okay. And then you have some bias current here. What happens is this current will be related to that bias current. It's like a current mirror between this one and that one. Instead of a single transistor, you have two transistors, that's all. Okay. The same goes on the upper side. In fact, I'll have the same bias current here and there. So here also between these two transistors and those two, it's a current mirror. Okay. So it is getting biased with a fixed bias current, which is what we want, right? We want a constant current bias in the transistors. But the signal voltage here and there will be the same, and it provides an infinite input resistance. I'll continue from there, but this was I think actually this now I would say it has fallen out of favor because it's not easy to accommodate all these transistors in a 1 volt or a lower supply voltage. But when the supply voltage was higher, this was used quite widely. This was actually reported in one of the leading journals when it was published in the 80s or something like that. So to make class AB biasing for CMOS opamps. Okay. Well, I'll describe it a little more, but basically the idea is you get infinite resistance here like a common source amplifier. You have the same signal swing here and there so that both the currents are dependent on the signal. Both the upper and lower currents are dependent on the signal. And you have well controlled bias currents through the devices. Okay. You can think about them. I'll continue from that later. Any questions? This is called class AB biasing.